Here we're going to look at how to calculate entropy changes if we have a liquid or solid, temperature changes, or if we go through a phase change from, say, a liquid to a gas. And the way we're going to do this is to start with our definition of entropy change, which is the integral of dq reversible over T, where T is absolute temperature. The idea is if we're at state 1 and we go to state 2, if we pick a reversible pathway and then the heat transfer at any point divided by the temperature at that point integrated gives us the entropy change. And so to get the heat transfer, we're going to use the first law. So let me write down the differential form. First law for a closed system. So Q reversible and work reversible. So work reversible would mean pressure times the differential. Now it turns out changing pressure has very little effect on a liquid or a solid. We don't change the enthalpy, we don't change the entropy, we don't change the volume, etc. So to a first approximation for a liquid solid, we can write this as minus the differential of PV. Now, what I'm going to do is take this term, bring it to the other side of the equation, and we'll see that we have on the left du plus dpv, and u plus pv is h, so this is dh is dq reversible. dh for a liquid or solid is heat capacity, Cp, times dt. So that means if we now want to calculate the entropy change, and again, let's rewrite our definition, and dq reversible is Cp dt over T. Heat capacity for liquid or solid does not change much with temperature, some reasonable temperature range. So if that's a constant, then the entropy change, starting temperature, our final temperature. Here's entropy change as we change temperature for liquid or gas. Well, the other case we want to look at now is entropy change for a phase change. So we want to look at entropy change for a phase change, and an important aspect of a phase change is it takes place at constant temperature and at constant pressure. So our equation for first law is identical. We're at constant pressure, reversible process, and so we have dH is dq reversible. And difference is dH is the enthalpy change for a phase change. So this is a number, right? We're at one temperature, and so at a given temperature this is going to be a constant. So when I go back to my definition of dq reversible over T for a phase change, dH over T integrated. T is a constant, so with delta H over T. And so for a phase change, entropy change, and again this is per mole, enthalpy change per mole divided by absolute temperature. Again, let's emphasize this is per mole.